Hey everyone, it's Dr. C. This is part 2 of the video answer key for the Hour Exam 2 from Spring 2018. So let's just get started. Part 1 went through, I believe, the first 14 problems. Problems 15 and 16 we're going to cover later in the semester, so don't worry about 15 and 16. The remainder of the problems on this exam deal with the acid-base chapter, chapter 16. So let's just get started here. All right, make sure you know definitions, both the Bronsted definition, the Arrhenius definition, and then also how, in this case, there's information about a strong acid or a weak acid or things like that and how they react in water. So a Bronsted base is a hydrogen ion donor. That is not correct. That would be a Bronsted acid. A Bronsted base is a hydrogen ion acceptor. Here's the Arrhenius definition for an acid. Acids produce hydronium ions in water. That is true. That's the Arrhenius definition. All right. Now, number 3, read this carefully. Strong acid, that's important. All right, the hydronium concentration is approximately equal to the initial concentration of the acid. And so what do we assume about a strong acid? Exactly right. 100% ionization. So all of that strong acid, so we just generically represent an acid as HA. This would be the acidic proton in water. Bronsted acid, hydrogen ion donor, producing hydronium. Acids produce hydronium, and then the conjugate base of that acid. Now, for a strong acid, we assume, and this is a really good assumption because the Ka values are very, very large, this reaction goes to completion. So it is true that the concentration of hydronium, because it reacts completely, 1-to-1 ratio, will essentially be equal to the initial concentration. And for our purposes, that's what we're going to assume. Technically, it's going to be very, very slightly less because the reaction technically, might only go 99.99% to completion. So they won't be exactly equal, but for our purposes, we will assume that they are. Okay, so it looks like 2 and 3 are true. That would be choice D. All right. We did talk about conjugate acids and bases. Here's an example. Here's the acid in our reaction that we wrote here, and this would be its conjugate base. So the acid donates an H+. What you're left with is its conjugate base, which will have one less H+. So this would be the conjugate base. So what would the conjugate acid be of that? It would have one more H+, which would be H2CO3. So that would be H2CO3 functioning as an acid, donating an H+. When it does so, we produce hydronium. And what's left behind, HCO3 minus, because we lost an H+, we'll have a minus charge, negative charge. That is its conjugate base. So when the acid donates an H+, we are left with its conjugate base. All right, so make sure you can differentiate those. All right, next one, 19. Make sure you know pH and pOH. Now, at 25 Celsius, this is a good equation to know, and it will be on the equation sheet. pH plus pOH is equal to 14. So you do know that low pHs correspond to acidic solutions, pH less than 7, acidic, or pH greater than 7, basic, and equal to 7 would be neutral. That's at 25 Celsius. Now, so if basic pH is greater than 7, what can you say about pOH? And if you have to plug in some numbers, plug in a pH of 10, see what you get for pOH, but pOH for a base will be less than 7. Okay, so kind of like, think about acidic. Low pHs are acidic, less than 7. Same thing for pOH. Low pOHs, because it's a negative log scale, would be a high concentration of hydroxide. All right, so a basic solution will have high pH and low pOH, or, relative to 7. Okay, so think through that. We'll do a little more with pOH in class as well. All right. Now, don't forget, now we're moving on to 20. Don't forget that these are all aqueous reactions. And so the equilibrium of pure water is always present. And we've looked at that in class, what we call the auto-ionization of water. And when we write the equilibrium constant expression for that reaction, which looks like this, one water molecule functioning as an acid, the other functioning as a base, we get hydronium and hydroxide. The equilibrium constant expression for this, we do not include the pure liquid, so it just has hydronium and hydroxide. That will be on the equation sheet as well. But don't forget about that equation. For all of these acid-base reactions, that equilibrium constant expression will always hold. So, if we know the hydroxide concentration, we can always solve for hydronium or vice versa. Now, if you're not told otherwise, but you are this time, assume we're at 25 Celsius. Kw at 25 Celsius is 1 times 10 to the negative 14th. Plug in your hydroxide. Now you'll notice that your hydroxide is a really small concentration. So this is certainly going to be an acidic solution. We're going to have a significant amount of hydronium ion. And I calculate hydronium of about 0.036 to 2 sig figs, which is choice C. All right, so here's another point. So one, know how to use that equation, pretty simple. The other point is, this is an acidic solution. We have more hydronium than hydroxide, but we still have some hydroxide. It's not very much in this case, but it's always a balance. Neutral, hydronium equals hydroxide. Acidic, more hydronium, less hydroxide. And then conversely, basic, more hydroxide, less hydronium. It's always a balance between those. All right, cranking right along here. Now, it's really important that you can recognize strong acid from weak acid, from strong base, from weak base, because you need to know what you're calculating the pH of. So make sure you know your list of 6 strong acids and your list of 6 strong bases. And this acid, now a tip-off that this is an acid is it starts with hydrogen in the formula. Okay, so when you see that, you're going, oh, that's probably an acid. That is one of the 6 strong acids. All right, so the nice thing about a strong acid, as we've talked about above, is that they essentially ionize completely, and that is what we're going to assume, 100%. So when nitric acid donates an H+, 100% to product. Acids produce hydronium, and then we will get the conjugate base of that acid. Note the negative sign again. Since we lost an H+, what we're left with will be an anion, a negative ion. Now, you don't have to write all this out, but I'm going to do this for sake of argument. We're starting with 1.25 molar. Products would be 0. This reaction goes all the way. All right, all of the acid goes to product. Now, that is an assumption. It's probably more like 99.999%, but you get the idea. All right, now, the cool thing then is that hydronium concentration is just the initial concentration of that strong acid. So you could shortcut this problem and get to the answer more quickly than I have, but we have the hydronium. pH is the negative log of the hydronium concentration. Now, be careful here. Since our concentration is greater than 1, the log of 1 is 0. Now that this is greater than 1, we are actually going to get a negative pH. And you can actually have slightly negative pHs. You can also, for strong bases, have pHs greater than 14. Generally, and this is where you always hear it, pH is between 0 and 14. That's generally true, but not always. All right, and I do have my calculator here. 1.25, you take the log, it is 0.0969, but we need to make that negative, so the correct answer is C. Okay, so a strong acid, concentration greater than 1 molar, will have a negative pH. All right, next one. Let me just give a little bit more space here. I try to leave you guys enough space on the exam itself. Sometimes I could probably use to leave a little bit more. So again, recognizing strong acid from weak acid, from strong base from weak base. Again, we know that this starts with hydrogen in the formula. It even tells you that it's an acid. Okay, is it one of your 6 strong acids? No. So it's a weak acid. The Ka value also tells you that it's a weak acid. So remember, and you don't have to write this out, but it's going to help me explain what you need to think about here. Acids, hydrogen ion donor, acids produce hydronium, and then the conjugate base. Okay, now, typical weak acid, and again, this varies depending on the weak acid, varies depending on the concentration of that weak acid, but approximately weak acids do not ionize very much. They only ionize about 1%. That means 99% typically stays as the weak acid. Only 1% goes to our product ions. 1% ionization. All right. So what are we going to have in the greatest amount? Yeah, the weak acid. 99% stays as weak acid. We only get a small amount of product, hydronium and nitrite, the conjugate base. Now, hydroxide, if this is an acid, it produces hydronium, so you're certainly going to have more hydronium than hydroxide. That's out. And we don't even get this species. That's choice E. So this is kind of testing your knowledge of a weak acid, and that weak acids only ionize to a very small extent. We'll say they partially ionize, but by partially ionize, typically that means only a very, very small amount, about 1%. Oops, I kind of jumped way ahead there, didn't I? All right, a couple more problems here. Again, identification. This one should be pretty easy. It tells you it's an acid, but again, we'll watch for starting with hydrogen in the formula. The other thing that we really haven't seen on this exam, but watch for, are carboxylic acids. COOH, that's a carboxyl group. And those are weak acids as well, so watch for that. The other thing that tells you that this is a weak acid, very small Ka. All right, so this one, we are going to have to set up an ice table. And again, it is important that you can write out the reaction because you need to know particularly what your products are. Let's get rid of that for now. All right. And again, to guide you, know the definitions. Acid, hydrogen ion donor, that's Bronsted. Acids produce hydronium, that's the Arrhenius definition. Initial concentration of that acid, 0.05 molar. Let's assume there are no products before we've started. Even though we're not going to get very much product, this is a really small equilibrium constant. Even though we're not going to get much product, we will get a little bit. So this cannot be at equilibrium with zeros at our product. So some reactant has to go to product. All our coefficients are 1, which is nice. Okay. Our Ka value, products over reactants. Again, we do not include pure liquids. Plug in your Ka, and our products are x times x, which is x squared, over 0.05 minus x. Now, very, very important assumption, and I can guarantee you will see this on the exam. 100% guarantee. Small Ka, this reaction lies very far to the left, very far toward reactants. So very little reactant goes to product. And again, assumptions for calculations are really important. One, kind of the thought process is just something to really know for problem solving. Making approximations, making estimations, powerful for problem solving. And it's a skill you do have to learn. And so strong acids, even though it's not quite right, the approximation that they go 100%, really important. Weak acids, it's the opposite. They hardly go at all to product. So we're going to assume that our initial concentration does not change much. And as an approximation, we're going to assume that initial concentration stays the same. And so that greatly simplifies our calculation while being a good approximation, and it will not impact our calculation to any significant extent. And we'll figure out that's true in the next problem by calculating percent ionization. So now all we have to do is multiply by 0.05, take the square root to solve for x, and you should arrive at a value of x of 4.95 approximately, times 10 to the negative 6 molar. And what does that equal to? Yeah, that's hydronium. This is an acid. Acids produce hydronium. Now, here's where it gets a little bit tricky. Don't fall for the trap that once you solve for x, you're done. Almost always for ice tables, x is not the completion line. You are close, but you haven't crossed the finish line yet. And so this problem, we certainly have not crossed the finish line because we want the pH. And so we need to take the negative log of that number, the hydronium concentration, and we get a pH of about 5.31. All right. Acidic, yeah, less than 7, so we're good that way. This is a pretty darn weak acid. That Ka value of 10 to the negative 10th is really small. Remember, most of our weak acids are kind of in the 10 to the negative 5th, maybe 10 to the negative 6th range. So this is a really weak acid, so we expect the pH to be quite small, or quite high for an acid. Still acidic, but high for an acid, because this is a very weak acid. All right, last one. Percent ionization for this acid. Okay, now, this is the same thing as checking the 5% rule. And so we made this small x approximation here. So we're saying x is small compared to the initial. And that's also the amount that happens to go to product. So that's also our percent ionization. All right. So the part that goes to product is x. The whole amount that we started with is the initial, part divided by the whole. That's a fraction. Multiply by 100 to get a percentage. So our percent ionization is simply x divided by the initial, part that reacted, divided by the whole amount we started with. That's a fraction, multiplied by 100. And I already forgot my number. I think it's about 4.9. There we go. 4.95 times 10 to the negative 6 molar. We started with initial concentration of 0.05 molar, multiplied by 100 to get to a percentage. And it looks like, how many sig figs do we have here? 3? Yeah. Let's say 3. It looks like I expressed my answer to 3. And to 3 sig figs, 0.00990%. Now remember, these leading zeros are just telling you where the decimal point is. Those are not significant. This would represent our 3 sig figs. So our percent ionization is D. Now, remember, and I back a couple of problems, I said your typical weak acid ionizes about 1%. This is not quite your typical weak acid. This is a really weak acid. Does that make sense? A weak acid? So the percent ionization is quite low. If we round up, it's actually 0.01%. All right? 99.99% stays as the weak acid. Only 0.01% ionizes to product. This is a really weak acid. And that percent ionization tells us that. Now, last question, and I will stop talking. Was our assumption valid? Yeah, very much so. Remember, what our typical assumption is that X needs to be, and that's a less than sign. Sorry, it kind of got compressed. Less than 5%. Okay, X has to be small compared to the initial to say that, well, let's just assume the initial stays the same. So X has to be small. Typical rule of thumb, less than 5%, that won't impact our calculation very much, and our answer will come out very close to the actual answer. Again, this is an approximation, so our answer might be slightly off, but if X is indeed small, our answer will be very close. In this case, X is really small. So even if we solved a quadratic, I bet you our answer would be almost identical to what we ended up with. All right. That gets us through the exam. Now, as I mentioned, problems 15 and 16, I'm saving for later in the semester. So we got a little bit more done in the acid-base chapter for the exam that you're going to see on Thursday. So don't forget, you will also see strong bases and weak bases on this upcoming exam. So make sure you can identify your 6 strong bases. Make sure you can identify what a weak base is. Go back to the pre-lecture. In the pre-lecture, I talked about weak bases being a class of compounds called amines. Ammonia is the simplest example. All right, so make sure you can identify those. Make sure you can calculate the pH of either a strong base or a weak base as well. So identify and calculate the pH. All right, and know the difference. You know, what makes a strong base a strong base? What makes a weak base a weak base? It's kind of the same thought process as strong acid versus weak acid, but bases produce hydroxide. Okay, so that's the big difference there. All right, enough for now. Good luck on the exam, and I will see you soon in class. Take care.